Okay, thank you. So, as said, I will present data structure for computing persistent homology. It's a joint work with Jean-Daniel Boissonnat and Tamal Day. So first I will give some motivation. Why do we study topology? Why do we use persistent homology? So homology is the study of the global features of a shape. So by global features, I mean connected components, holes, voids, and higher dimensional shapes. So this is really useful in topological data analysis, in machine learning, visualization. So on the right of the screen here, you have an example coming from chemistry, where you have a conformation space of a cyclooctane molecule. It's a 8-carbon cyclic molecule that is coming from organic chemistry. And if you attach 3 coordinates to each of the carbons, then you get a 24-dimensional vector for each conformation of the molecule. And then you can twist it, and you can modify the shape in a very with a few degrees of freedom, and then you get a shape in dimension 24. And if you project it in 3D, you get this kind of weird object, which has a very interesting topology. So I will come back to this example later. So first I will introduce homology. So given a shape here, it's a torus. A good way to picture it is to draw a loop on it and try to modify it by sliding along the shape. So you can have like small modification, and then you can slide it this direction, or you can reduce it to the small loop on the right here. But you cannot deform it to this loop because it goes around the hole. So homology will try to catch this phenomenon. So in the discrete case, that will be interesting for us because we are computing this, we have a simplicial complex, and it's a set of simplices. Here I draw edges. As you can see here, you can characterize a loop by a sequence of edges. And I consider the abelian group made of the formal sums of p simplices. So in the case of edges, it's just like a sum of edges with coefficients. And in that case, this loop becomes the sum of these 6 edges. All right. And I define on this abelian group the boundary operator, which simply assigns to a simplex the alternate sum of its subsimplices of dimension 1 less. So if you have a triangle here, okay, it has an orientation, it's not really important. But if you apply the boundary operator to a triangle, then you get the sum of its edges with some plus minus. I won't go into the details. And for the presentation, I will consider only Z2 coefficients instead of Z coefficients. So here your Ki are between 0 and 1, and then you have the addition of Z2, because it gives a better intuition. And then, okay, the plus becomes a minus because 1 and minus 1 are the same in Z2. And you also lose the orientation in that case, so you have a nice looking loop. And so you have your boundary operator. And the interesting objects, I said they were the loops, but I've presented only arbitrary formal sums. So as you can see, loops are actually in the kernel of this operator, because if you take the boundary operator of a set of edges forming a loop like this, then you get twice the sum of twice every simplex, every vertex of the edges, because the boundary of this edge will make this vertex appear once, but the boundary of this one will make it appear a second time. And as we are working in Z2, then this will cancel out and be 0. So the cycles, which are the interesting object we want to deform along the shape, are contained in the kernel of the boundary operator. So we also consider the image of the boundary operator. So I took the same cycle here, and it's in the image of the boundary operator of dimension 2, because you can consider this set of triangle, and if you take the boundary of it, then every edge inside will cancel out because two triangles are sharing it, and only the one on the border is remaining, and this gives you the intuition of why we call it the boundary operator. A fundamental property is that if you compose twice the map, okay, you reduce the dimension by 1, but if you compose the map, then you get 0. So the boundary of the boundary is indeed 0, which means that the image BP is included in the kernel ZP. And then you are allowed to define HP, which is the PS homology group. Okay, so that's an algebraic construction, but there's a very simple explanation. Suppose you are given a cycle here. So your cycle is in your kernel ZP, and you want to make it slide on the surface. You want to deform it to this one, let's say. So you consider the area that is covered by this cycle when you're sliding toward the bigger one on the exterior. And this is actually a set of triangle you're sliding through. And it means that the difference between this cycle in the inner part and the cycle on the exterior part, the difference is actually a boundary. So when you take the quotient here, you basically say that this cycle here and the one you can deform it to are the same. So they are in the same equivalence class of cycles you can, meaning you can deform one toward the other. So this is like the very unprecise explanation of homology. And for the expert, actually, when I say sliding along the surface, it's more about homotopy theory, but we don't really know how to compute. It's way more complicated. So homology is a weaker version, and we can do good computation with it. So any questions so far? Okay, good. And then, how do you recognize the fact you have a hole in this shape? Then you have this cycle that you cannot deform onto this cycle, and you cannot deform it onto a cycle that you can that you draw here. So this object, this group will have different classes of cycles that are not equivalent. And then you can recognize the number of holes, what I call like homology feature before, thanks to it. So now, what is persistent cohomology? You don't compute homology in a single simplicial complex anymore, but you consider a family of growing simplicial complexes. So suppose at the beginning you start with a bunch of points, and then, so if you look from really close, you see all these points. But then if you look a bit further away, then you kind of see things merging. If you consider like a coarser geometric scale. So you start to draw edges between vertices and triangle too. And you see that homology features are appearing too. And then you keep going further away, and then things are merging. And this hole, for example, is disappearing here. And if you keep increasing the distance from the object, then you see only one big black dot. And then the homology along these inclusions is changing. So first you have a lot of connected components, then you have two holes, then only one, and then eventually you have just one big black dot. So persistent homology is actually recording this evolution of homology by assigning at every moment the corresponding homology groups. So here it counts the connected components, here it counts the loops. Here you have only one loop left. And also linking the different homology feature from one moment to the other. And so there's a like full algebraic theory around it, but all you need to know is that you eventually get a diagram recording this the evolution of homology. And you have one bar per homology feature. And as you can see at the beginning, in blue you have the connected components, so you got many. But very quickly you're drawing edges in your simplicial complex, and then you're killing connecting components, so the bars are stopping really quickly, and you have only one long bar that is the only one connected component that survives all along the filtration. And in red you have the holes. So they are appearing a bit later because you need, of course, a few edges. And you see that the hole B here has a shorter life than A because it's smaller, geometrically speaking. And then from this diagram, you can read that, okay, you're very likely to have like one connected component and one big hole, one smaller hole. So that's a very interesting information you get from the persistence diagram. So the only thing we need to do is what is a simplicial complex. So I guess everyone here knows that it's just a bunch of simplices, and you can define like combinatorially what is the boundary by assigning to a triangle the set of its edges. So that's all what we need to know. And very naturally, you've seen that we have this deconnection between the simplicial complex that carries the combinatorial information. So we have one face that is linked to the other because they're sharing some subface. So it's a very local information, more geometric, more combinatorial too. And we will represent it by some data structure here. I mentioned the simplex tree. That is the work I've done with Jean-Daniel in 2012. That carries the combinatorial information and allows boundary computations. So I won't go into the details here, it's another work. And I'll be interested in the way we represent the cohomology group here. So very naturally I use a matrix, but that's I will be a bit more precise in the following. But the only thing we have to know is that we are separating the two structures because they are fundamentally of a different nature. Okay, so let's compute persistent cohomology. So as I said before, we have like a growing sequence of simplicial complexes that you can see simply by ordering the simplices of one big final simplicial complex, and you just add them one after the other. And every time you add one simplex, you have to update the homology group, because sometimes you create holes, sometimes you fill some. So I will use for this this cohomology matrix that represent the cohomology group of my complex. So you have one for each dimension P here. And the columns are attached to the simplices, τ1 to τn. And the rows represent cocycles that are dual object to cycles. I won't go to the details again, but you can see them as cycles. And they just like attach to each simplex a value. So I will call a column the annotation attached to the corresponding simplex, and the rows will be cocycles. So I got my p-dimensional homology group for my simplicial complex Ki, and now I add a new simplex sigma I plus 1 to get the simplicial complex ki plus 1. And I want to follow this arrow and update my cohomology groups. So how do I do this? I first compute the boundary of my simplex sigma I plus 1. I found the corresponding simplices in the matrix, and I sum their annotation. I get one vector here. And now I got two possibilities. Either my annotation vector, the annotation of the boundary, is equal to 0. And this means that the simplex I'm inserting will create a new feature. It's like putting the last edge of a cycle, then you create a new feature. You are independent from the former cocycles you had in your homology group. And you simply need to put a 1 in the bottom right of your cohomology matrix. If my annotation vector is non-zero, then I have a lowest non-zero value here at the index k, which means actually that my new simplex sigma I plus 1 is destroying something. It's like putting the last triangle to fill a hole, so you destroy a homology feature. So you need to proceed to a reduction of your matrix. And the associated reduction is of this form. So to each column associated to a simplex tau j, you need to subtract the annotation vector times this coefficient. It's actually a Gaussian elimination. So I don't go into the details of what is going on at the homology level, because I'm just describing the algorithm and it will take too much time. But you just need to think about creating something by putting a new row, as I did earlier here. Creating something is basically adding a new row, and destroying something is doing a reduction in the matrix, so as I'm just getting 0 on a row phi k here. So any question about the algorithm? Okay, so how do we implement this algorithm? So let me first introduce the compressed annotation matrix, which is a sparse representation of our cohomology matrix. So you're given a matrix with integer coefficients, and we represent it this way. So as you can see, every column is sparse, every row is sparse. So if you take the column B here, you have only 3 non-zero elements, and you find them here. So you have a coefficient 9 in the row 1, you have a coefficient 3 in the row 2, you have a coefficient 8 in the row 7 here. And you have also like transversal pointers to be able to traverse a row of a given index. So if you want the value of your cocycle number 2, then you can find them in the row. And we also have like a compression phase where we store only once columns that are identical. It's the case of A and C here. So A and C are identical, so we store the column only once. And we use a disjoint state data structure on top to be able to record the fact that A and C are in the same, have the same column. So if you are looking for the annotation attached to the column C, then you go in the disjoint state data structure, which is like a union find. You go on the root, and then you find the vector attached to it. All right, so let's sum up what we said. Okay, so we have a simplicial complex. Here it's a simplex tree, and we have a compressed annotation matrix on the right. And here is the overview of the algorithm. So you had a new simplex sigma I plus 1 in your complex. So you compute the boundary in your simplex tree data structure. So you have an algorithm for that. So here, if you have the tetrahedra, is the tetrahedra 2, 3, 4, 5, then you have the boundary, the triangles are here. And then you can jump in the matrix in order to find the corresponding annotations. What you're doing here, you sum them up. And then you have two possibilities. Either you have 0, and then you need to put a 1 in the bottom right corner, which is very simple in your data structure because it's just adding one element in the bottom right, like here, for example. Or your annotation vector is non-zero, and then you need to proceed to a reduction. So the reduction is of this form, and you actually simply need to find all the non-zero value of the row phi k you're reducing, because you're multiplying by this element, which needs to be non-zero. So you can find, thanks to the transversal pointers, all the non-zero value of phi k, and then sum to the corresponding columns this element. So this way you have a very sparse, sensitive implementation of your algorithm, because you don't need to traverse all the zero values, and you just directly go to the non-zero value you want to reduce. So we have a complexity analysis for this that involves quite a few variables. So you can see some inverse Ackermann function for the union find. You have some complexity for computing the boundary. So you can get this quite complicated expression. But if you simplify a little bit, then you're reduced to this expression. So you're computing the percent homology of a simplicial complex with m faces. And this time is the time for one insertion. And Cmax is the maximal number of non-zero value of a column. And Rmax is the maximal number of non-zero value in a row. So it's a sparse data structure, and you get a sparse complexity analysis. And K is the dimension of your simplicial complex, and it comes from the fact that you're summing up annotation vector corresponding to a boundary. So you have this expression, and we have noticed that in practice your homology group is extremely sparse. And for example, I haven't found any example where Cmax and Rmax are bigger than 20. Even if your simplicial complex has like 100 of million simplices. And the dimension is also usually small because it's the dimension of your simplicial complex. And you basically cannot have a simplicial complex of very big dimension because the number of faces would be huge. So we also introduce a reordering heuristic for the simplicial complex, because sometimes when you have an inclusion from one simplicial complex to another simplicial complex, you have many faces appearing at the same time. So here you have an example. And here you have two suggestions for ordering your simplices. And it's two possibilities. They both work, but one is way better than the other. So anyone has maybe a suggestion about which one we should take? And why, of course? Yes? Sorry? Yeah. Yeah, absolutely. So as you can see in the first one, in the transition phase, let's say from the homology group of this guy to the homology group of this guy, then you see that you're increasing the genus by quite a lot for eventually filling up all holes. When here, every time you create a hole, then you fill it directly. So in that case, in the transition, you have 3 holes to eventually have none. But in that case, you make only 1 at most. And if you run the algorithm I've described, you can actually see that your matrix is getting bigger in that case than in that case. So this one is indeed better. So we have formalized this idea into a heuristic by traversing the Hasse diagram of our simplicial complex. So I won't go into the details again, but we are basically going to the maximal simplices and adding simplices which are next to each other. This way, we don't create small holes, but we just put big bricks next to each other every time we add a simplex, and we have like a recursive phase to reorder the sub-dimensional faces. But you'll see in the experiment, so this is purely heuristic, but you'll see in the experiment that it works pretty well in certain cases. Okay, so here they are. So we have compared our algorithm with state-of-the-art implementation of persistent homology and persistent cohomology, which are dual. In our case, it's persistent cohomology. So this implementation is the library Dionysus, computing persistent cohomology. And these 2 implementations are fat using matrix reduction on a cohomology matrix for the orthogonal and on the homology matrix. So these 3 implementations are the most efficient you can find. And we have used, as you can see, a wide range of real value data and natural data of big size. So you got millions of simplices every time, and different kind of construction, Rips complexes, witness complexes, alpha shapes. And CAM is the compressed annotation matrix. So if you compare our implementation to the persistent homology algorithm of FAT, you can see that on certain example, FAT is as fast or slightly faster than our implementation, but it doesn't scale to certain examples. Like as you can see here, the time is huge, when in our case it remains small. And it's quite hard to explain why this example doesn't succeed as well in homology. But my interpretation is that they are first higher dimensional, intrinsically higher dimensional, and also they have lots of maximal dimensional simplices, for which homology has problem to deal with. So okay, so we are scaling up quite well. So Dionysus is indeed slower. Even if it's the cohomology algorithm, it's the same. The algorithm is the same in nature, but the implementation is a bit more naive than the compressed annotation matrix, and the running time speaks by itself. So we are sometimes like a few hundred times faster. And finally, the persistent cohomology algorithm of FAT, which is an optimized version of the persistent cohomology in a completely different way than ours, is still quite substantially slower than our implementation. And the very good thing is that we have a very stable running time on all examples, all kind of simplicial complexes. And we are able to deal with 10 to, more like 5 to 1 million of simplices per second on a normal machine. So it's fast. And okay, some more statistics. The compression phase helps reducing the size of the matrix by quite a big factor. And it reduces the number of algebraic operation in the matrix by a huge amount. So this is 46 times less field operation in the matrix. The average length of a column is very small, and the maximum is 18 on one big example here. So as I said, I haven't noticed a bigger value than 20. So Cmax and Rmax are coming from the complexity analysis. And the reordering, as you can see, is sometimes very efficient. In that case, it's a RIPS complex where you have a lot of simplices appearing at the same time. And then you have some other statistics. And we are also quite insensitive to the coefficient field we are using. All right, thank you.
Are there questions? Please use the microphone, please.
So I have a question about the ordering of the reordering of the simplices. And this may be a naive question, but so to what extent are you allowed to reorder the simplices, and to what extent is the ordering fixed by the input data, like close points have to have simplices appear before faraway points?
Yeah, the reordering, so you have this simplicial complex and you got filtration values on each simplex, which dictate the time of appearance of each simplex. So you're allowed to reorder only within the same value. So if you use, I've presented different examples. If you use an alpha shape, for example, you will have very few simplices with the same filtration value. But in high dimension, usually you have RIPS complexes or construction of this kind, where you're only allowed to use low dimensional predicates to define your simplicial complex. So with a RIPS complex, for example, then you add one edge, and then suddenly you have a huge amount of simplices coming, like lots of triangles, tetrahedra, and so on, because they are all induced by only one edge. So they all come at once with the same value. And they are also localized on the same place, because you can more or less assume that all edges have different lengths. And so when you reorder these simplices, usually it's within the same geometric region. And so that's the one appearing at the same time. So do I answer the question?
Yeah, thank you.
Okay.
Another question?
Very nice work,
Thank you.
I missed something in the matrix representation, but for sure. So I probably missed something in the explanation of the matrix representation, but where is the gain over, for example, using the standard representation for sparse matrices, one of the standard representation? Yeah,
the compression phase is the most important thing here, because this is pretty standard sparsification method. This is what you will do with a sparse matrix. The thing here is that the persistent cohomology algorithm, and it's not the case of the persistent homology algorithm. So the persistent cohomology algorithm is very specific and has this streaming kind of fashion, where you just like feed your matrix with simplices. And as you can see in the algorithm, in the way you update it, you treat a column exactly the same if you treat two columns with the same value exactly the same way, because you have this very specific kind of Gaussian elimination, basically, when you modify your matrix. That's, I would say, the most important optimization of this structure is the compression phase. Because, yeah, you basically replace a bunch of column addition by a simple search in a union find.